So roughly where I'm going with these lectures, I think these are the right slots. We've slightly rejigged the program for tomorrow and Wednesday. So today I'm going to talk in general about some aspects of atmosphere-ocean coupled modelling. A little bit of a focus on more the short range, but not exclusively. And then the two slots on Wednesday will be looking more at coupled prediction systems on different timescales. So in the morning, a bit more of a focus on the short range, and then in the afternoon, evening, a little bit more of a focus on the longer range. So that will include seasonal and decadal and climate timescales. And I should say I'm by no means an expert on those things, so I'm sure there'll be people in the audience who have more expertise in those areas than I do. One thing I should say as I touch on them, I'll try and focus particularly on kind of the new frontier aspects of those systems and recent results of interest, and particularly those aspects which are relevant for the operational oceanography community, whether that's related to initialization of the ocean component, for example. And the separation between some of those talks may be a bit fluid, particularly if I run out of time today, and aspects of systems versus applications versus models may be a little bit vague at times, but I'll try and stick roughly to that kind of outline. So today, a general introduction and some motivations for coupling, whatever we mean by that, and I'll come on to that. A bit of a sort of history of where coupled models have been used, very brief, particularly as I'll say a bit more in some of the lectures on Wednesday. And then looking at advantages of coupling, or at least potential advantages in our systems, potential disadvantages, with perhaps a bit of a focus on issues relating to initialization, which is always a big issue, and we've heard something about that already from various speakers. And practical considerations for coupled model systems. I think in everything I say, particularly because I'm quite close to the sort of operational side within the Met Office, I'm not quite the person that Greg was talking about who's called at 5 in the morning if there's a problem, but I'm not so far from that. So I think the sort of practical considerations and the real issues of running these systems operationally will kind of influence what I say in quite a few of these areas as I go through. So, as I've already said, coupling is quite a widely used term, and even in the oceanographic community, we've heard examples of people talking about ocean wave coupling, ocean biogeochemistry coupling. John this morning mentioned open ocean, coastal ocean coupling, and sometimes people even use it to talk about coupling between the ensemble and your deterministic model in some kind of hybrid DA scheme. So the whole variety of cases, as I say, the focus of these talks is mainly on ocean-atmosphere coupling, and mainly on the global scale as well, partly because other people have touched on some of the regional domains, partly because the global is more of my area of focus. And beyond what systems we're coupling together, people sometimes talk about one-way coupling or two-way coupling. So reflecting whether or not there's a genuine two-way feedback between different systems. Now, in my mind, the sort of boundary between one-way coupling and just a forced system is slightly unclear. So most of what I'm talking about really is what I would consider to be two-way coupling, where the feedbacks are able to happen in both directions between systems. So I've already said ocean-atmosphere coupled systems have sort of been more traditionally used on longer timescales, the ones I'll be talking about on Wednesday in particular, but they are becoming more common on the shorter timescales, so what we might call short range, sort of out to sub-seasonal timescales. And I'm going to spend a lot of this lecture by talking about ocean-atmosphere coupling in general, and some of the motivations for adding increased complexity into what are already quite complex ocean systems that we run. And it's a question, do we really want to increase the complexity of those systems further? So in general terms, whatever our sort of Earth system model, there are lots of possibilities for the way that we use our finite computing resources. Baylor gave us a kind of estimate of kind of how much computing resource we have, and we can choose to use that in lots of different ways. Resolution is one, as up there on the top right, and Baylor gave us lots of examples of where resolution can have an impact. But we can make our systems more complex by adding in different Earth system components over here. We can make more use of observations, whether that's putting more resource into our data assimilation schemes, the way we process our observations, more different sorts of observations. And we can also do things like increasing our ensemble size, or perhaps for sort of climate runs, things like that, increasing the length of our simulations. And these often get sort of posed as sort of competing places where we could put our resource. But I think we've already started to see this week that actually a lot of them are very interrelated. So how we use our ensemble will feed back on our data assimilation within certain formalisms. Impacts of resolution may only really be realized if you have high enough, impacts of coupling and complexity may only be realized if you have high enough resolution in some of your component systems, for example. So often it's not a case of one or the other, but which things you need to use in combination. So I think there are at least 3 different reasons why we might just think about how adding an extra component to a system make it more complicated. And I think a lot of these depend on the in a sort of operational sense, on the remit of the centre in which you're working, and what sort of products you're funded to provide, or what you're asked to provide by your owning department or government or whatever it is, because that will impact your choices on all these things. So one reason we might have for adding complexity is if we already run a model like an ocean model in a force mode, then by adding an atmosphere model, even if we're not interested in providing atmosphere products per se, that might help improve the forcing for the ocean model, and therefore improve your short range forecasts. If you look at it more from an atmosphere side, if you're in an NWP forecast center, your primary focus is running an atmosphere model, then you might not even be interested in providing any ocean forecast products, but you might want to consider adding an ocean model as part of the system in order to capture some of these feedbacks. But a third reason is if you're actually interested in providing new products. So I think an example of that might be adding a sort of prognostic sea ice model to an ocean system, for example. A lot of ocean models originally didn't do that. But if you're actually interested in producing forecasts of sea ice, or an equivalent example in the atmosphere might be some sort of atmospheric chemistry and air quality forecasts, then you want to add a component into the system in order to provide forecasts that perhaps you wouldn't otherwise have been able to provide. But as I say, those decisions are very dependent on what the remit of your operational centre is, and there'll be no sort of one-size-fits-all kind of answer to those questions. So here's just another example of the different elements of the Earth system. We've seen very similar schematics as we've been through the talks already this week. And there are lots of different parts of the system that we might want to model more accurately and capture the feedbacks. But here the focus is, as I've said, mainly on the physical ocean and physical atmosphere. So for the climate timescales, I think it's fair to say general circulation models started to sort of more routinely include an ocean component from round about the 1970s as a result of a recognition that coupled processes were important. You wanted to capture things like ENSO, the recognition that the ocean was a kind of long-term integrator of changes in the climate system, and that you wanted to be able to model the impact of ocean circulation changes, for example, in the ocean, a key example being the Atlantic meridional overturning circulation. But those early models had quite a few problems because it was difficult to have a model which would give a adequate representation of current climate. So by that I mean, for example, the sea surface temperatures and temperature structure of the ocean, at the same time as having a reasonable net flux balance at the top of the atmosphere that seemed close to zero, or at least consistent with a small climate change warming signal. And during the 90s, it was quite typical to provide sort of flux corrections to your ocean model in order to your climate model in order to get a system much closer to present-day climate. And only as ocean modelling improved, and I think one particular example that's thought to have been quite relevant in that is the parameterization of eddies, allowing the adiabatic removal of potential energy in the system, along with increases in vertical resolution, for example, in the models. So that meant by about the 90s, most of the climate models were running without any flux adjustment or flux correction. Then seasonal models is probably the next timescale on which forecast systems have been dynamically coupled with an ocean. And that's really a recognition of the fact that ENSO provides the major source of seasonal predictability. Mike's going to be talking a lot more about ENSO later, and we've already had Tony talk a little bit about it, so I won't say too much more on that. And also that the upper ocean heat content anomalies in all parts of the atmosphere are particularly significant for seasonal forecasting. And then decadal forecasting is less mature, really only the last, I suppose, 20 years that's started to become a bit more of an area of activity. And again, the ocean has a big impact, so the deep ocean information increasingly important for initial conditions and predictability of the AMOC, for example, but external forcing, so solar variability and greenhouse gases playing a big role. I'm going to touch more on all those things tomorrow, so forgive me for just skipping over them now. And as I say, a lot of the rest of what I say this morning is going to be more about short-range forecasts. So why might we want to couple an ocean to an atmosphere for timescales of 1 to 2 weeks, I guess, is the kind of timescale we're mainly thinking about. So I suppose the simple answer is that the real world is a coupled system. So that's a clear sort of motivation for why you would want to do it. It allows you to capture feedbacks between the ocean and the atmospheric boundary layer that you can't easily capture just using independent atmosphere and ocean models. I'm going to come back to all the bullet points or the majority of bullet points on this slide in the future slides, so I'll just very quickly skip through them for now. Another example is representation of the diurnal cycle and the impact that has on mean fluxes. It gives you more control over the surface forcing that you've got. You're not just getting it from an independent system or perhaps a kind of independent organization. You have some control over what's happening with it, and you can understand how that's changing. It avoids some of the problems with ocean forcing. And we've seen a bit of this already in various talks. So there are lots of problems with the way that we force models, typically using bulk forcing, but assumptions about what that forcing is and the impact that that has on your system because of the lack of relaxation, well, the lack of feedback to the surface forcing, which gives you an effective sort of relaxation to what you're applying. And then I'll say something about consistency with other coupled modeling systems on different timescales and how that might help in understanding errors. So this comes back to something we've seen a few times. The sort of traditional view on the right-hand side is that sort of atmospheric forcing is what drives the sea surface temperature anomalies, certainly on longer timescales and on larger spatial scales. So sort of at a basic level, stronger winds mean kind of more mixing, lower SSTs. And that's what the right-hand side is attempting to show. But over recent years, and this Brian et al. Paper is an example, so the correlation between sea surface temperature anomalies and wind stresses using observational products has been shown to be positive over most of the ocean, which is an indication that on these small time scales and smaller spatial scales, it's actually the ocean mesoscale activity which is driving the atmosphere rather than the other way around through modification of the atmospheric boundary layer. And those kind of results have been reproduced in climate models, although generally not until you've gone to higher resolution. So these are examples from some Met Office Hadley Centre climate models, different atmospheric resolutions, N96, which is, get my numbers right, sort of 100 and something kilometre resolution, N216 more like 60 kilometers, then down to something kind of closer to 30 kilometer resolution for the atmosphere. And then the ocean resolutions, the top one is a 1 degree ocean resolution, and then 1/4 of a degree and 1/12 of a degree. And on the bottom, you've got a similar sort of observationally derived product to the one that I showed before. So at least when you're getting to what we'd say was sort of eddy permitting ocean scales, so 1/4 of a degree, that second plot right, you're starting to get more evidence of generally positive temporal correlations for most of the ocean, and something which is looking more like the observational product. That's not to say that these kind of correlations are capturing all of what's going on, certainly at the sub-mesoscale that we were talking about. So it's not saying that we're capturing everything, but at least it's showing that in many regards the ocean models are getting to the point where they can reproduce what we can see in the current observations. And there's various discussion last week about the sort of contentious nature of some of the conclusions about the way these processes work with the mesoscale eddies impacting the atmosphere. But certainly there have been a number of papers showing the correlations between what's going on in the ocean and what's going on in the atmospheric boundary layer and above. So this is an example from Franger et al., where they've taken composites of different ocean eddies and looked at correlations with so wind, cloud fraction, rain rate, for example, in the atmosphere, and seen significant correlations in those things. And then thinking about the mechanism of what's going on, and then the impact that might have on the ocean, how it might feed back on the ocean. And I guess in many ways you'd say these are only sort of genuinely sort of coupled effects that you maybe need a coupled model to take account of if they are both impacting the atmosphere and then also feeding back on the ocean. Otherwise, you could say, well, actually, all the atmosphere model needs is some high-resolution SSTs, perhaps some high-resolution forecast SSTs from your previous day's ocean model is probably good enough for the atmosphere. But if we want to be looking at what's happening in both the atmosphere and the ocean at the same time, then it's these kind of feedbacks back to the ocean, which could be either positive or negative depending on different conditions, which are the important thing. And similarly, there's been work looking, and I think someone has showed these Minobi et al. Plots already this week, looking at the impact of sea surface temperature gradients in the North Atlantic on, for example, rain rate in the atmospheric model, showing that the resolution of the ocean model is very important to get those things right, and that the impact is not just at the surface. So that bottom right plot showing the impact on winds up to quite high levels in the atmosphere, up to the upper troposphere. So the modelled rain rates, and of course those will then feed back on what's happening in the ocean as well, are very sensitive both to the resolution of the SSTs, but also therefore to the position of these SST fronts, which may or may not be as good in your ocean model as they would be in a sea surface temperature analysis, which is much more tightly constrained by the observations. And these are kind of the sort of classic example of one of the feedbacks which affects coupled systems, and which you don't get in a ocean only or atmosphere only system, is looking at you don't get the impact back on the atmosphere in an atmosphere only system. Looking at the impact of tropical cyclones and the cold wake that you get behind them in the sea surface temperatures. And these are just two examples of some particular cases from 2016. On the right-hand side, showing the cold wake in the ocean component of the coupled model. This is an example run at the Met Office, but there are many similar examples previously. And you'll see that these are capturing a similar sort of cold wake to what's seen in the sea surface temperature observations on the left-hand side for the equivalent day. In fact, you might say, well, it kind of looks like the ocean's overdoing things, which it may or may not be. But you've got to remember that the satellite SST observations in these regions are not necessarily particularly good either, because of cloud cover associated with the storms And sometimes satellite SST products like OSTIA take a few days actually to catch up with what's actually going on because of sort of relaxation to climatology when they don't have observations. So these forecast SST anomalies may well be more realistic than what was actually captured in the what's given as observations. But again, I think the thing is here, we can see these things in an ocean-only system, but only in a couple model, or at least some attempt to feed those back into an atmosphere model through some mechanism. Will they impact the atmosphere forecast as well and have an impact on how the storm actually evolves at the time? Diurnal cycle is one thing I mentioned on that list. So whether or not we resolve the diurnal cycle has a significant impact actually on the fluxes. So these are looking at what happens with and without a diurnal cycle going into a reconstructed flux using bulk formulae. And you'll see that in areas of the ocean where there's a big diurnal cycle, actually the difference between using high frequency sea surface temperatures in the flux formulation compared to using a sort of daily mean as you might use in an atmosphere only model is quite significant. So you capture a lot more of the higher fluxes in the tropical regions particularly. Now that's not necessarily an argument for coupling. There are lots of ways we could try and mimic this. We could put a sea surface temperature sort of diurnal scheme into our atmosphere model or into our ocean model if we don't think that adequately captures the diurnal SST variation as it currently stands. But they're just examples of the kind of things that a fully coupled system finds it easier to get right. And this is one a sort of slightly more practical application. It's just based on something that I had available from some testing we were doing recently. And I think it's something that we sometimes forget in our operational systems or have no control over. But this is some changes in sea surface temperatures in testing of a new version of our ocean system. And the only difference here is so it's over a period of a month, so a reasonable amount of time. But the only difference here is that the sea surface temperature being used for the NWP model that was driving this ocean model has changed. So it was a new version of the OSTIA sea surface temperature product, which had some reasonably significant changes in parts of the ocean. And so this is just the impact that those sea surface temperatures are having on the atmospheric temperatures and humidities. And then when we use those to force the ocean in an ocean-only model, we see significant differences, which is really just making the point that actually a lot of these, what we might consider sort of coupled issues, are already there in our ocean-only systems. It's just we kind of don't have any control over them, so we have to live with them. But the benefit of going to coupling is that we can treat everything as a much more sort of unified whole and look at all these things together. I briefly mentioned the ocean forcing issue, and again, this is something that various people have mentioned in talks we've already had. So whether or not, for example, you use the ocean surface current when you're calculating the surface stress in your ocean model, and whatever you do in a force system, it's difficult to get that right. If you don't use the relative current, then you tend to get too much eddy kinetic energy in your ocean. If you do use it, you can often get too little. If you take account for the current feedback that on the atmosphere, so essentially by running a couple model, then you get something somewhere in the middle, which probably looks closer to observations in many cases. But there's no perfect way of doing that, and there have been various schemes that people have come up with to try and sort of parameterize a value of this kind of alpha of how much relative current you should use in your force system to capture what's going on in different parts of the ocean. And of course, all this depends on being quite sure about what your winds that you're using are already. And Mark sort of pointed out that we need to be careful to know exactly what impact the currents are forcing wind data set has already got in it. So these problems aren't insurmountable in ocean-only systems, but they're things that we certainly need to think quite hard about and how we deal with them. One thing that gets mentioned quite a lot as an advantage of coupled systems is what people often talk about as seamless prediction. So the idea that if we use a consistent ocean model on all timescales, from the very short timescales where we can see model biases starting to develop, right through to the longer climate scales where we can see some of the long-term climate signals and kind of climate drifts. So the idea that that has big advantages. It clearly has advantages in many cases in sort of model development and sort of technical infrastructure that we're building the same systems with associated complexity that comes with that. But it can also have quite big advantages in helping to understand biases or model processes which are relevant on all timescales. And at the UK Met Office, that sort of schematic is just sort of making that point. And at the moment, we use the same coupled model configuration on the right-hand side out from seasonal timescales through to centennial timescales. But at the moment, our short-range systems, so our atmospheric NWP and ocean forecast systems, wave forecasting systems, and our ensemble on sort of hours to days to week are still forced systems or independent systems. So the idea is that by going to more similar coupled systems across all timescales, it will put us in a better position to address some of the model biases and model errors on all of those timescales. So what I've tried to say there is give a sort of flavour of the potential examples of benefits of coupled systems. Obviously, there are potential problems, in fact, quite a number of potential problems. And how we see those as problems will depend on whether we're viewing these things partly from an atmospheric point of view or an ocean point of view. So from an atmospheric point of view, your atmospheric model may well see lower resolution sea surface temperatures than it would if it was just using a sea surface temperature analysis. And that's particularly true in a system like the one we're running currently, which is a 1/4 of a degree ocean. So it's quite significantly lower resolution than the OSTIA sea surface temperature analysis that our atmosphere model currently uses. And those SSTs might not just be lower resolution, they might well be worse because, for example, the Gulf Stream position isn't so good, for example. I think I'll come back to that in a second. And it's not just positioning of features in those sea surface temperature products that might be less good. We can get drifts in those which impact the quality. Initialization is a particular problem about how to do that, and the problem of initialization shocks just because different parts of the system are being initialized in a way which is not consistent. And the benefits of the coupling may not be immediately obvious if we haven't been working in a coupled system to start with. So aspects of these systems may effectively be tuned for running in an ocean-only or atmosphere-only mode. And then we need to think carefully about how those things have been done in a coupled system. And then lastly, some inconsistent physical constants or assumptions can have an impact in coupled systems. So again, I'll go through these on the next few slides in a little bit more detail. So this is an example on the sea surface temperature quality issue. So this is, this is the difference between the foam. So that's our 1/4 of a degree ocean. In this case, it's our forced ocean operational model. So the sea surface temperature differences in the North Atlantic, quite significant warm bias compared to the OSTIA product over a 1-year mean there. And so clearly that is a significant difference for what the atmosphere model is going to see, and that's going to feed back on the numerical weather prediction in the atmosphere. In fact, our coupled system is actually slightly better. So it doesn't necessarily mean that when we go to a coupled system, we see all of that degradation. Some of this improvement may well be coming from differences in the data assimilation windows rather than actually the coupling itself. But we can't necessarily assume that just because aspects of an ocean-only system are worse, that when we put them in a coupled system, they will also be worse. But clearly with a 1 degree ocean, you're going to give the atmosphere less detail in its sea surface temperatures and less accurate positioning of the Gulf Stream. And then something on sea surface temperature drift. So one of the things I said was the disadvantage of bulk formulations for forcing the ocean is that you don't have the feedback to the atmospheric fields. You're just prescribing things like surface air temperature, winds, humidity, for example. But actually in ocean-only systems, that can be an advantage because it helps to stop your models drifting too much, particularly on longer timescales, but even on shorter timescales. So we've quite often seen in our coupled and forced ocean configurations, which is essentially identical in other regards, that we see larger sea surface temperature drifts in parts of the ocean than we do in the couple model, than we do in the force model. So the aspect of bulk forcing can kind of work both ways. It can help in some ways to stop your model drifting, but as I've said already, it can be a bad thing in not capturing feedbacks that we would want to capture. And then 2 examples of initialization shock. So this is one of the other big problems, I think, in coupled systems, how to initialize them. Sea surface temperatures. So these are some slides from ECMWF, which are looking at aspects of initialization in their SERA system, so their coupled reanalysis system, which Keith briefly introduced last week. And something they've seen there was, and really the drive towards using this coupled reanalysis system rather than just initializing from independent analyses, what they see big jumps in the atmosphere. So on the bottom right, you've got the changes in the atmospheric air temperatures over the first 12 hours of the forecast, sort of verified against their own analysis. So you see some really quite big differences in atmospheric air temperatures. And those are really just being driven by differences in the sea surface temperatures when you initialize the system. So you have an atmosphere analysis which has been using a sea surface temperature product like OSTIA as its boundary condition. You then suddenly initialize a coupled forecast using an ocean which has got quite different sea surface temperatures in different places. And those sea surface temperature differences kind of almost immediately feed into the air temperature differences that you see on the bottom left-hand side. So that's kind of sort of stating the obvious, that if you suddenly change your sea surface temperature, you'll suddenly change your air temperatures above that, and kind of how much of a problem that is maybe a matter of a debate. But clearly there are similar examples where you can introduce shocks to your system just because of changing aspects in your initialization. There's a slightly different example that we saw with sea ice in our system. So these are 5-day forecasts of sea ice from both our global coupled system with a 1/4 of a degree ocean, which is the top left, and then our ocean-only system with the same ocean, the bottom right there, the foam system. And depending on how good the projector is, you probably notice that the coupled system looks a lot less like what I've labelled as the truth, which is just the verifying analysis, which is very closely tied to the observations because we assimilate the sea ice concentration. So in this case, we see that the global coupled system has quickly adjusted from the truth it was initialized to. And in this case, it's due to an inconsistency in the freezing temperature formulation between the ocean-only system, which provided the ocean-only analysis for the coupled system, and then the coupled system itself. So this isn't something that is a kind of completely fundamental problem of initializing coupled systems from ocean-only or an atmosphere-only analyses. But it just stresses that you need to be very careful to make sure that everything in those systems is consistent. And in practice, that's very, very difficult to do, and essentially it is therefore a problem of initializing from independent analyses. I probably won't say too much on this one. It's something that it's probably more an issue for longer term simulations, climate simulations, for example. But this is a quote from the Campen et al. Paper in 2008, and just making the point that even if you've got individual component models which all ensure conservation and have a sort of consistent set of approximations, if you put those models together, even though they're internally consistent on their own, you can create conservation issues within your coupled system, which are an issue for timescales where conservation is something you care more about, like climate timescales. And that can be as simple as the fact that you've got a different value for your sort of latent heat or something in the two different models, but they can be a lot more subtle than that as well in the way you're treating. Well, this is an example looking at the way we're treating latent heat, heat content of precipitation and assumptions that different models are making about that. But I'll just skip over that for the moment. So those were potential problems of having a coupled ocean atmosphere forecast system. And a lot of those potential problems, or some of them, can be addressed by looking more carefully at the way we do the initialization. So if we're no longer initializing from independent ocean and atmosphere analyses for a coupled system, but we're instead initializing from a fully coupled initialization system. So this is sort of straying slightly more perhaps into the sort of system aspects of these things. But if we have a coupled initialization system, then obviously we can capture all those sort of feedbacks we were talking about before, not just during the forecast, but during the analysis cycle as well. It means we can allow atmosphere observations to influence the ocean and vice versa. And that could happen indirectly through coupling in the model background, or going slightly beyond that in the outer loop of the assimilation scheme. And that's what most people tend to refer to as weakly coupled data assimilation for the initialization. But it can also be more direct through using sort of coupled covariances in your model, and that tends to be what people call strongly coupled data assimilation. So these are all potentially good things, making use of different observations near the atmospheric ocean interface to allow a consistent set of ocean and atmosphere states. So you don't have any shocks when you start your forecast because everything's in consistent balance. However, it is inevitably more complicated technically and sort of scientifically to work out how to do that. I'm not saying too much about coupled data assimilation because I'm not sure how much is going to be covered in other talks, but these are just some quite nice examples from ECMWF again about just looking at how an observation in the ocean is able to influence the atmosphere during their analysis cycle. So they use an outer loop weakly coupled data analysis scheme for their coupled model. So this is just one observation at 5 meters in the atmosphere, in the ocean, a temperature observation, and you can see it feeding up to impact the atmosphere state above it. And then this is a similar example of a wind atmospheric observation influencing the ocean during the analysis cycle. And similarly, I showed before this sea ice example from the Met Office system, and by having a coupled data assimilation system, in this case it's just using the background from a coupled model, not using outer loop coupling, so it's still a very weakly coupled data assimilation system. But by moving from the top left, which is initializing from independent analyses, to the top right, we remove this problem of inconsistency we had previously in the freezing temperature, and we get a sea ice concentration which is much more similar to the previous ocean-only system and to the verifying truth. So there's a lot of benefit from coupled initialization, both on a kind of practical sense. It forces us to keep things consistent, but it also allows us to make use of observations in the optimal way in both the atmospheric and ocean boundary layers particularly. getting towards the end, I thought I'd just say a little bit more about some practical considerations of ocean coupling on short timescales particularly. Again, this is perhaps sort of moving more into the systems side rather than the pure modeling, but I think the things are very related. Inevitably, coupled model systems are more complicated. They usually require some sort of coupler technology to deal with the exchange of fields between the different models and to interpolate from different grids, for example. They may well require additional computational costs, particularly if you're if you're an NWP center who doesn't already run an ocean model, then adding in an ocean model to that system to improve your atmospheric forecast is going to increase your costs. There's some consequences for data assimilation if you're moving to a more strongly coupled data assimilation for initialization. And one of the big ones of those would be how you deal with differences between assimilation windows, which are traditionally often shorter in the atmosphere, so for example 6 hours. And we've heard a lot about much longer assimilation windows in the ocean this morning as an example. And again, those things aren't necessarily sort of showstoppers, but they certainly make things more challenging working out how to deal with them. So often, generally the case that there's a bit more latency in some of the ocean observations, and particularly when you've got issues of, for example, the orbit-corrected altimetry. Pierre-Yves was explaining about that you've got a delay before you get the most high quality, and that's part of the motivation for going back extra days or several days in order to capture that. And then testing and making decisions about model upgrades is quite complicated in a fully coupled system. The coupling technologies themselves, I won't really say very much about them, but the various different approaches. Either you can do everything sort of in-house and deal with your own coupling code to exchange fields between your models. You can use specific couplers like OASIS 3 MCT or ECMWF, and then also kind of layers on top of that, like OSTIA, which bring you kind of closer to being able to sort of flexibly plug and play different models together. In practice, it's quite difficult to get to that point because you've got to really understand all the assumptions your different models are making and exactly which fields you're exchanging. And the choices of all these things will have impacts on kind of how you sequence your models. Are you running two models at the same time, or are you running one and then the other? How you do your interpolation, how frequently you exchange fields between the models, whether you're dealing with any sort of implicit aspects of the coupling. So they all need thinking about, and it's really a sort of science in itself addressing those kind of issues and how to control and run models in a complicated multi-component system. This is just a sort of schematic which is attempting to show some of the complications of our weakly coupled, so only weakly coupled data assimilation system. But and I don't particularly want you to kind of understand what's going on here, but we've got model time on the x-axis and operational runtime on the y-axis, and just these little boxes are all different assimilation cycles that we're running, similar to some of the examples that John showed this morning. So it all becomes quite complicated to work out how to implement operationally in the most optimal way. And as I've said, they're making decisions about model upgrades is difficult. You can't necessarily test your full system at the highest resolution, for example. So you've got to be careful to not make assumptions which aren't true at higher resolution. How do you make decisions about some things are degraded, some things are improved in your atmosphere and ocean models? Which of those determines whether or not you should go with an upgrade? But I think I would argue that all those kind of things already exist. Actually, we already make decisions about whether our currents are more important than our sea surface temperatures or whatever it is in our different systems. So it's really only a sort of extension of existing problems. I don't think there's a sort of completely new aspect to that in the ocean atmosphere coupled context. So I think this is my last slide, Jacques, which is sort of a slightly different one. Having talked about the potential benefits and problems of coupled systems, maybe some of these things have come through in what I've already said, but I sort of feel we talk too much about coupled models or coupled model benefits, because actually, maybe that sounds like a slightly controversial statement, but on shorter timescales, probably the majority of those impacts you could obtain by other sort of what I'd term looser forms of coupling, and I've mentioned some of those already. So you could put sort of diurnal schemes in your model. You could run with a slab ocean for your atmospheric forecast model, or you could give the atmospheric forecast model yesterday's sea surface temperature forecasts. So there are lots of approaches like that, sort of halfway houses towards coupling, which would all give you some kind of benefit. They still add a complexity, but they're less than full coupling. And sort of the other side of the coin is we probably talk too much about coupled model problems, because actually we already have lots of internally coupled schemes within our models. There may be some aspects of atmosphere ocean modeling which are unique because of the different timescales of the models and history of model development, but actually we already make lots of decisions about how different schemes, whether that's in an atmosphere model, how the cloud scheme interacts with the radiation scheme, or whatever it is. There are all sorts of coupled model decisions that we already have to make in a way we're not really talking too much beyond that in a full Earth system context. And I think regardless of these pros and cons, these benefits and disadvantages of coupled models, if you're an operational center that already runs atmosphere and ocean forecasts, at some point it just becomes easier to run a single combined fully coupled system. I think if you're not, then I think some of these potential benefits and problems are perhaps slightly harder to call, and it might be longer before everyone's running fully coupled systems for everything. But I think I will leave it there because Jack's standing there.
Thank you, very interesting. We take short questions. Fabrice?
Fabrice, you have lots of opportunities to ask me questions.
Please, student.
Yeah, about you mentioned the coupling between the atmosphere and the ocean. What about the interface, like the wave, and do you consider like coupling with the wave model as well? Or?
Yes, so I haven't actually said much about ocean wave coupling in any of my lectures or in my book chapter. I think I had expected a bit more of that to be covered in I think Fabrice's talks. Yeah, that perhaps is a little bit of an omission. For our systems, we are looking towards putting a wave component into them, and certainly I think that's an important piece of the picture in getting the whole atmosphere ocean surface interactions right, and probably many of these kind of examples of potential benefits you can't get quite right until you have the wave component in there. So yeah, I think that is really key.
Okay, thank you. Apparently, that was
Excellent.
Thank you again.
Okay.